So Alannah Hallas, who's an associate professor in physics here at UBC. And so within the pollution intermittent issues. Lots of expertise into the living from characterizing materials. So I'm really excited to learn more with a whole range of different techniques that we create. So it's
Thanks, everybody. Thanks for my introduction and the opportunity to speak in this seminar series. We already attended lectures and presentation. So I'm excited to give my spin on that. Looking my research to discuss the characterization, immediately I realized it should be this problem of biweekly oxides, because this is a problem where we really have to bring to bear an entire range of characterization techniques to get the types of insights that we need. And then saying what about these materials really makes it to make characterizations. Specifically today, I'm going to try and focus on, I'm going to show a lot of different data. The techniques that I'm going to really emphasize are the X-ray-based techniques, which are best suited to this. So without further ado, once folks, this data can come from my side of things, because seeing my institutional chemistry materials now probably many times. Before that, thanks for measuring composition costs, if you may not have seen this material before. Want to know kind of this introduction to the concept of biochemistry materials. And from that introduction, it really helps to contextualize when we talk about disordering a material, what are we really about? And so this is a legal transcript image of the disorder state. You're visualizing there is the idea of a robot. So our kind of blue balls or balance, you form some square arrangements. Every once in a while, you see some of this one, and there's a bit of body in the same, or body like shaping, or situation at different so and speak everything around. And the point to this system is that disorder cannot be limited to just the vacancy itself. You actually have to think about the effect that that disorder is having on its surrounding environment. So it's not just that the longest effect and about is actually you can see what's happened here. So the vacancy actually shifted that position somewhat to try to compensate for the energetically unfavorable atoms. All different species. So this is our kind of usual image when we think about disorder and solids and materials. This type of really significant state properties to a material, and categorize those effects as kind of positive or negative or friend or foe. So when where these substantive disorder is pretty much friend, in the type of substantial defects there are politically concealed and of charity silicon. So silicon was extremely cheap, like it had absolutely no defects whatsoever. Will be insulating to be used for electronics applications, and it's really through the very controlled introduction of substitutional things that silicon achieves non-product properties that make it useful for biological projects. Really, it's only research area of quantum materials. We often think of disorder as having a very negative character. And the reason is that very low levels of disorder can easily dissolve complex quantum states that originate in materials. So probably this is very much true is a lot of quantum stable materials have very entangled quantum states the limit of certain. These materials, because the interest in physics is really low temperatures, the energy scales of even very weak disorder become substantial enough to completely overshadow physics even and so you in that field, you know, our best to completely eliminate what's possible. So my group's research, I'm actually in the middle of this. A lot of you will know from research and discovery grant programs. This is sort of our investigator funding in Canada for faculty at universities. And I'm in the middle of my second discovery grant, and I wanted to come up with a framework for the research that I does. And what I really saw as kind of the underpinning attribute of all the research that I'm interested in is this concept of disorder. And I can imagine the spectrum. So you have the things that have virtually shockingly low levels of disorder, So want to understand why we see materials innately fluid form with small methods of different reasons these this resilient to those events. And as our learning continues, we work towards systems that have higher and higher levels of discernment, including life. This beautiful colored like language fields. This is the material that I'm going to be describing in my talk today. But if you're interested in any of those other categories of some materials, so this is probably actually, you understand most of the important properties of a high energy oxide just by kind of considering the aspects of this representation. So you see is again a regular arrangement of atoms, just before we have those blue atoms are forming a square arrangement. Here we have the kind of three-dimensional kind of cubic arrangement of atoms. And you can see if we focus in on this smaller lighter atom, which is our oxygen, she has a completely ordered arrangement. There's nothing disordered about oxygen's organization. What is disordered is the identity of the cation, the metal element, center of that oxygen. And that's represented by the different flows that you see on this image. So in fact, there are specifically 5 different columns that are shown in this description. Those represent 5 unique chemical species. And so the kind of core attributes of high energy oxide is that they should be crystalline, they have well-defined crystal lattice. But they both have this degree of chemical abundance. We won't see that those cations are distributed in a way that's completely new. That is to say that 2 adjacent seats, the identity of the chemical element occupies them is completely uncorrelated. So 1 in 5 chance on state and 1 in 5 chance on state. So if we're very long length scales, you have this enormous degree of so this is a tidbit that's was born from corresponding with alloy type materials. Alloys are just it's not something of materials but the and the Entropy Oxide field was born in 2015 on this first rocks discovery. And anyway, it was appreciated that to characterize this type of crystal structure with this degree of chemical disorder, you need a lot of information coming from different sources. So by nanoscale, what I mean is what is the sort of spatial resolution over which the technique gives you information. So if we want to come crystallinity, we need to look at time scales and really thousands of angstroms because we want to know that for many repeating units of the structure that the average symmetry is well restricted. And so that's what a technique like X-ray diffraction gives its insight into, based on writing techniques, structural interference conditions that are being fulfilled by that average structure, this repeating motif. And at the opposite end of the length scale divide, so now we're looking at things that occur on each length scale. So like spacing, characteristic spacing between 2 atoms in solid. We can look at techniques like atom chromatography, which is actually a structured technique, looks at the evaporation off of a tip. So you fabricate a tip of your material of interest and you send those atoms through a spectrometer where you can divide them according to their mass. And from the material flip for the atom to you can reach completely where the atoms started in that tip. And so we end up with images like these, where these subtle patterns are telling you every time an atom of that identity. And doing this atom tomography, one thing that we can immediately understand about these attributes is that we do have this chemical randomness. So there's not transforming any obvious clustering or segregation of the products. I really do for the kind of really simple. So that's an example of a real species that was diffractionism is not several species. Actually have an enormous complement techniques provide correlating information, including some of the techniques that have been featured already in this characterization UBC features. I'm going to introduce a couple of techniques above and beyond what's shown here today to answer a specific question. And you just mentioned in physics, it is customary and physics makes simple to interact with questions. And I'm going to encourage you to do so. Like, so if you don't, I'm not if you have a question, please just. So, the additional kind of way that we can define our entropy oxides is by quantifying their configuration attributes. So we actually interrogate a little bit about entropy, by entropy oxides, like what is the source of entropy? So the source of entropy is the number of possible arrangements of the cations on the lattice. So if I have two different types of ions, there are fewer possible arrangements of those two cations as compared to there's many more possible configurations as they could be arranged. This is the quantity that goes with the size of the system, so it's useful to normalize it into some meaningful units. We are generally normalizing units to release that actual and we see is that if you think of if we just take a simple kind of expression of the Boltzmann entropy formula, this was the sum of the both species was a and it's the functional contribution of that species, x sub I, times the natural log. And so if you using the on your calculator, to find out what these values are, you'll see that they tend to give so maybe 1 and 5 identical constants depending on how many species you have. It's easy to see this formula is going to be maximized when the function of each element is equal to one another. So if I have 1% of one species and 99% of another, the configuration entropy of that is much, much smaller than the corresponding case where I have a 50-50. So for our 5 constituents, which is the example that I had shown in this when our sum is when each of those 5 constituents is present 20%. So I just want to give a little bit of a flavor on why this topic of high entropy oxides has generated so much excitement in the field of material science, where it is that enthusiasm. It's obviously pretty complicated to make and study a material like this. And the juice would however be worth the squeeze, but you would like to see that it's actually doing something useful and interesting. And one case where this is this beautiful work from 2018, where looking at incorporating these entropy materials into lithium ion material. So what's being measured here is this capacity. It's how much charge can be stored it's the nature of signal. So that's charging and discharging signal. And so for a material to be useful in this context, you would like that capacity to first be large, even more importantly, you would like it to be stable. Meaning that you don't want your battery life to become partial as it was after using. So this passage here is plotted for 4 different oxidative shapes. Green from the yellow, the red, and the blue have 4 cations that are sharing their lattice, and the one that has 5 cations has highest entropy. What you can see is that only the highest entropy material has the stable signal stability, so its capacity is maintained. And then the second kind of example comes from thermal conductivity. So this is measurement of the thermal conductivity as a temperature, and again plotted corresponding to materials entropy. So we have our lowest entropy, kind of most conventional materials here. What you see is that as we're adding more and more cations into our material, the thermal conductivity is being monotonically getting pushed lower and lower and lower. Lots of contexts in which it is useful, lots of applications where it's useful to have a material with a long-term. One example is for something like a power plant, or even the energy side of side. It's really remarkable about the highest entropy material, the one that's labeled as 1.79 R, is that its thermal conductivity is actually lower than you would expect from a system. System channels still not as thermal conductivity lower than the material as about. Sorry. So one of the things that I'm interested in is what is the role of synthesis method dictating the properties of these materials? Do synthesis methods produce materials that are sort of in the same way before discovered? And I think we know about synthesis methods and which average of certain materials. It's very natural to wonder how does such a discovered material vary as functions? And that's what we're going to talk about. So to answer this question, we do need to narrow down our focus to a little material. And for this, we choose our prototype material, spinel high entropy oxide. So spinels have the generic chemical formula PB204, so the oxides, they are high entropy oxide, and it will be noted. So the axis holders here representing the two different cell lattices that exist in this illustration. So one of those lattices shown here has a tetrahedral formation with oxygen, and the reduction interval is octahedral formation with oxygen. So this is the decision. The material that we're going to explore is primarily cast in this kind of superconductor. Since everything in the 3D transition model block went across from chromium up to we have this 3D transition models right in the middle of the flat chromium. And their special characteristic, the reason we were specifically interested in that combination of elements, is in every one of those ions in the oxide, we made a certificate magnetic. And so the future property we're going to explore is the magnetism of the material. So in our spinel structure, if you do a little bit of charge counting, you find out that to reach charge neutrality, you need to have a mixture of bivalent and trivalent, 2+ and 3+ cation species. That's going to turn out to be important later. And we form spinel form when the 2+ cations is on the peak state, the 3+ cations is on the peak state. They actually aren't forced to do it. They can invert. Remember, inversion you can think of as an additional potential source of HP.
Sure.
There we go. Sorry.
Oh, no problem. Okay. All cations are expected to be magnetic. And importantly for this study, all of these materials in general, spinel materials, are highly amenable to being formed by a wide range of synthesis methods. So if we want to be able to compare the effective synthesis method, we need to have a material that can actually be made by more than one technique. And spinels are fantastic for this because not only can they be made by one technique, they can be made by a whole host of techniques. And this is certainly non-exhaustive, but these are the 5 techniques whereby we have successfully produced this material. So we've grown exactly that chemical composition of a spinel using these 5 methods. And so I'll read them just quickly. There's solid state synthesis and high pressure synthesis. These are 2 solid state techniques. So the material is staying in the solid phase throughout the synthesis process. And we're relying on diffusion for the chemical reaction to proceed. Then the final 3 techniques, hydrothermal, molten salt, and combustion, are all crystal growth methods that take place in solution. And under different sort of conditions. So hydrothermal has high temperature and high pressure. Molten salt uses ionic diffusion to form a material. And combustion synthesis actually involves a very violent exothermic reaction under which the material is formed very rapidly. And so the way that I've organized these techniques is according to a rough hierarchy of what we expect in terms of their thermodynamic and kinetic factors. By thermodynamic, I mean that we're accessing the material's ground state. That is that the techniques sorted towards the left, like solid state, should most reflect the 0 temperature stability of that material. Whereas very high reaction kinetics means that the reaction is proceeding rapidly and that ions can perhaps be locked into kind of metastable configurations that would not be thermodynamically stable. This is a rough sorting. So when I say that a reaction proceeds rapidly, I think it is useful to show you what I mean by that. So this is a video of a combustion synthesis. So it's a real-time video. It's not sped up. Okay, so this is successful and slightly a failure. The reason it's slightly a failure is because most of our product has ended up on the top of this hot plate. So the idea here is that there was a solution that had in it dissolved salts of all of our precursors, so those 5 different transition metal cations in a solution with a fuel. And when that solution is boiled down such that the ratio of fuel to solution becomes like a kind of critical ratio, a spontaneous reaction will occur. And the crystal growth, the phase formation here is happening in a matter of, if not seconds, perhaps microseconds. So it's very, very fast. And we can imagine that locally within that combustion reaction, at the moment of combustion, the temperatures are locally reaching temperatures significantly higher than we could ever achieve in a conventional furnace, but they're also cooling to room temperature exceptionally fast. So it's a near instantaneous process. And as I said before, we can actually make that spinel high entropy oxide by these 5 different techniques. So these are just X-ray diffraction patterns. I'm going to say a little bit more about X-ray diffraction and X-ray sources in just a second. But for now, the main thing that you can just notice is that the kind of general shape of these 5 patterns is very similar to one another, reflecting that they have formed into the same crystal structure. They have the same diffraction conditions. They're obeying the same Bragg conditions. Okay. So before we can fully dive into the head-to-head comparison of our 5 different samples, we should first get a baseline of what this material does under its kind of usual conditions. And so for that benchmark, I'm going to select solid state. Again, it is sort of our most thermodynamic method of sample preparation, but it also turns out to be the sample that we prepared first in my lab. So it's the one that we just had the greatest sort of body of information on to build a comparison with. So I mentioned that we're going to be using magnetism as the functional property to explore how synthesis dependence evolves in a material. So this is an example of a magnetization measurement, a stability measurement. And this is performed in a magnetometer in our lab. So these are quantum design instruments that allow us to vary temperature and magnetic field in situ. And through that, we can build up a picture of the magnetic response of the material. We can specifically look for magnetic phase transitions and evidence of what the magnetic state might be. So in this case, what you see here is a measurement between, it's actually a very large temperature range. It's 0 and 600 Kelvin, so well above room temperature to close to absolute 0. And we see that there's a significant anomaly that onsets at about 400 Kelvin. And that anomaly is the magnetic ordering transition. So that's where the material is going from being paramagnetic, not having any coherent magnetic order, into some sort of state where the spins have a special alignment. And the 2 data sets here are performed under different conditions of the magnetic field. So yellow is what we call field cooled. That means that the material was cooled down in the presence of a magnetic field. And black is what we call zero field cooled, where we first cool the material down and then apply a magnetic field. And so the fact that these 2 curves don't overlap with one another immediately gives us insight into what that magnetic ground state is. It tells us that that magnetic state also has hysteresis. And so this is immediately kind of pointing us in the direction that this material has some sort of ferromagnetic character. And so to get additional insight, we can do the same type of measurement. So we're measuring the same property, but now instead of measuring it as a function of temperature, we're going to measure it as a function of applied magnetic field. So the way that we do these measurements is we start at 0 field and we sweep up to the maximum field. We come all the way down to the negative maximum and then back to 0. And so that's called a hysteresis loop. And if a material has 0 hysteresis, we don't expect to see any gap in that data. We would expect that the direction of the field increasing or decreasing wouldn't matter. The presence of hysteresis means that the magnetic state inside of the material depends on the history of the field that it was exposed to. And there are certainly classes of applications that actually require both there are certain types of applications where you would want to have a material that was able to switch very, very easily. Whereas there are other types of technologies where we would like, once we kind of encode a magnetic state into a material, we would like that to be resilient against things like temperature fluctuations and environmental conditions. So one is not inherently better than the other, but it is a useful characteristic of a material. And so what we see here is that what I just said, the presence of hysteresis, that can be also kind of quantified by this term of coercive field. That's the size of the field that I have to apply to overcome the material's hysteresis. So it's basically the width of this here. And that's really small. In this material, it's kind of at the order of 1/100th of a Tesla. It's tiny. But what we do see is that magnetization measurement, when we normalize it into these units of Bohr magnetons, so that's the size of a magnetic moment of a single unpaired electron, it's saturating at a value of around 1.5 Bohr magnetons per FU. So FU is formula unit. Notice that our formula unit, so we're talking about spinel materials. Spinels have a chemical formula of AB2O4, which means in one formula unit, there are 3 cations, A plus 2B. And that means that we have in a single, just if I took one unit of my spinel, I have 3 of those 5 different transition metals. And remember, those were iron and nickel and chromium. These are all very magnetic elements, and they have very large magnetic moments just by themselves. Actually, every single one of those elements in an oxide, you would expect it to have a magnetic moment larger than 1.5. And there's 3 of them in a formula unit. So this value 1.5 is actually very small relative to the formula unit of a spinel. And the only way that we can understand that size of the magnetic moment is if it's partially being canceled out. So there must be some partial anti-alignment of the moments in the material, giving rise to a net moment, but one that is smaller than the total moment. Okay. So we give that type of magnetic arrangement, one where there is a partial cancellation, but still some net moment, that gets the label of ferrimagnet in magnetism. Okay. I would like to just kind of bypass a little bit our neutron scattering work because I'm eager to get to our X-ray work. The main thing that I just want to say here without going into the details is that from neutrons, we can actually arrive at a microscopic picture of how those spins are arranged. So we can validate that assignment that this material is ferrimagnetic. And what we find in detail is that there's an anti-parallel arrangement between the spins that are on the A side of the spinel and the spins that are on the B side of the spinel. And it works out that the spin on the A site is actually larger than the spin on the B site, but there's twice as many of the B sites as there are A sites. And so the end result is that 2 times B is greater than A. And the moment that we actually extract from this neutron scattering measurement is in excellent agreement with the value that we get from bulk susceptibility. So from this, we feel like we have a very good grasp on what the magnetic structure of this material actually is. Okay, yeah.
So non-disordered case, we have one kind of cation.
Yeah, so the question, just in case people online can't hear, is whether it's ferrimagnetic in the non-disordered case. 99% of the time, yes. So it depends on the specific chemical composition. But spinels like iron nickel oxide, iron chromate, nickel chromate, they are all ferrimagnetic and they have variable ordering temperatures kind of between about 100 Kelvin and as high as 800 Kelvin. And then there are very few exceptions. I believe cobalt 304 is antiferromagnetic, but it's kind of just one out of many. Yeah. Okay. So I'm going to move into the X-ray section of my talk, and I wanted to briefly introduce the kind of difference between lab-based X-ray experiments and synchrotron-based X-ray experiments. And so I want to talk about how do we actually produce, how do we go about producing X-rays for material science? So option A, which is the option that I've actually already shown you example data of, that was powder X-ray diffraction data collected in my lab, is to use a lab source to perform usually a diffraction experiment. And so the way that X-rays are produced in the lab is that you are producing electrons in a cathode, and those are actually produced by thermionic emission. And those electrons are accelerated across a potential difference, and they strike an anode material, so a negatively charged material, which in our case is going to be metallic copper. And when those electrons that are very, very energetic impact onto our anode material, they actually knock out core electrons from the copper. And as an electron decays back in to fill the missing hole, electrons are produced with characteristic energies. So did I say electrons? Sorry, X-rays are produced with characteristic energies. And so a specific type of X-ray that we use in our lab is a copper anode, and we're using the K-alpha emission line, mostly K-alpha 1 with a little bit of K-alpha 2 mixed in. And so this is a great method for producing X-rays in the energy range of 8 kiloelectron volts. So that's the specific energy of that copper K-alpha. And what's useful about that energy is if you convert it into a wavelength, you find out that that's about 0.1 nanometers, so about 1 angstrom. And why that's important is that that is perfectly suited to match the diffraction condition in solids. So we can't have a wavelength that's much, much larger than the characteristic spacing in our material and still do diffraction. We need the wavelength of our X-ray to match the spacing in the material to fulfill the diffraction condition. And so copper does that perfectly. So to compare, first of all, this lab source, if I just held up the source of our diffractometer, I can easily hold it in my hand, and I would ballpark its size at being around 10 centimeters. To contrast, a synchrotron is, of course, an enormous user facility. The CLS's website very helpfully says that it's about the size of a Canadian football field. So that's a scale of about 100 meters, including the surrounding infrastructure, the beamlines. And the idea in a synchrotron is that we're still accelerating electrons. We're accelerating them around a ring, but they're being accelerated to much higher velocities. They're approaching velocities comparable to the speed of light. And electromagnets are being used to bend those electrons as they go around the synchrotron. And as they change direction, they emit very brilliant electromagnetic radiation, kind of orthogonal to the direction that they're being bent, or I guess parallel to the direction that they're being bent. And so synchrotrons can produce a wide range of X-ray energies. So I give the range here. This is, again, the Canadian light source in Saskatoon, as being as low as 15 eV to 90 keV. And so based on that huge range of X-ray energies, you can work on many different material science problems. You can do many different types of experiments. And so what you see at a synchrotron is that at various positions along the ring, there are these different beamlines that have they're built for different purposes. So they're optimized to monochromate a beam of different energies to do different type of spectroscopic experiments. Okay. So the specific beamline that we've been using a lot at the Canadian Light Source is called RIKES, and it's a beamline where we can do X-ray absorption measurements. And so this is a category of measurement where what we're going to measure is how much of an X-ray of a particular energy is absorbed by our material, or conversely, how much of that X-ray is being transmitted through the material or given off as fluorescence. And so what we learn from that is whether there is an allowed electronic transition within the material that corresponds to a particular incident energy. So this is very helpful if we just consider an example. So this is, again, our high entropy material. We have some photons of a particular wavelength coming in, and because pink is matched to an energy of our pink atom, some of those X-rays are being absorbed by the material, and so the amplitude of the photon that comes out the other side is smaller because some of those have been absorbed. And the reason they've been absorbed is because there's a specific electronic transition in that particular element that corresponds to that energy gap. So this is the energy across which an electron has to be excited. So often in our research, we're measuring on L edges, and an L edge is an excitation of an electron from a 2p state up to a 3D state, an unoccupied 3D state. And so what's really important about these absorption edges is that they are completely dependent on the atomic character of whatever the chemical constituent is. So your nickel absorption line is going to appear at a certain energy, plus or minus a very small difference, independent of whether it's in some molecular complex or in some extended oxide, a sulfide, a nitride. It doesn't matter. Nickel is nickel, and its atomic character is always going to be the same. And so what does actually change is how many holes there are in your 3D band. And so that's going to depend on the valence state of the specific element and its local environment. So in this case, this would be representing the case of something like copper 3D9, where there's just one hole in the 3D band. And there, the absorption is very, very simple. We only have one possible excitation that can actually be made. So it has a single very short spectral line. Actually, so there's just one. In fact, there are two, because there is a spin orbit splitting of these 2p orbitals. And so there's a small energy gap for electrons from this state here to this state here. So we actually see one edge that's twice as tall as this second edge. So that's the simplest case because there's just one possible hole for the electron to be excited into. It can, of course, get more complicated. And we can make the experiment more complicated by doing it in the presence of a magnetic field. So remember that our material is itself magnetic. And if we put our material in the presence of a large enough magnetic field, we can align all of the magnetic domains in the material. So all of our blue octahedral spins are all pointing in this direction, and all of our pink tetrahedral spins are all pointing in this way. They have a special orientation with respect to the direction of the magnetic field. And to complement the presence of the magnetic field, we're actually going to use circularly polarized light. So the light can be polarized with a left polarization or a right-hand polarization. And based on complex selection rules and the splitting of these 3D states in the presence of the magnetic field, what we actually see is that there's a preferential ability to create these excitations depending on whether the light is left or right circularly polarized. And so there's actually a difference between those two. And that's what the XMCD, which is X-ray magnetic circular dichroism, that's what the XMCD signal is. It's the difference between the left and right hand circularly polarized light. And so depending on whether left or right is bigger, you might see a negative or a positive XMCD signal. And it gives us specific information about the orbital and spin degrees of freedom in our material. So we learn something about the magnetism. And the great thing is that we can do both of these experiments simultaneously. So we can take the sum of the left and right circularly polarized signal. That's just our basic absorption. And the difference is our dichroism. So we've done exactly this experiment for our spinel high entropy oxide. And remember, our magnetic structure looks like this. But here, I've just drawn left and right spins. What we don't know anything about is, or not yet at least, is which of our cations are sitting on which of those sites. So where do the chromiums sit? Where do the nickels sit? And so on and so forth. So I can take exactly the example of chromium. So chromium has a very stable 3+ oxidation state. And it has just 3 unpaired electrons in its T2G orbitals. And so chromium is actually a bit complicated because there's many possible unoccupied states for those electrons to be excited into through the absorption process. And so when we look at the absorption spectra for chromium, we do see that it has quite a complex form. But what's shown below, purple, is the experimental data, and then below it in gray is what's called a multiplet calculation. So this is a theoretical calculation of what that spectrum should look like based on the assumptions of the charge of the cation and the local environment. And we see there's a really great correspondence. All the features are sort of in exactly the right position. And then if we look at the dichroism signal, again, that's the difference. We also see that we're able to well produce the shape of that signal. And the same goes for nickel. And so what we can conclude from this absorption measurement right away is that just chromium and nickel, their case is really simple. They're only occupying octahedral sites in our crystal structure. So they have very, very strong site selectivity. There's a very strong energetic penalty for those cations to sit on a tetrahedral site, so they really prefer to be octahedral. And cobalt is an example that's a little bit more complicated. It isn't as immediately obvious what it should prefer to do, so we actually have to consider an ensemble of possibilities. And if we only look at the absorption, the details are not important. These are three kind of possibilities of what cobalt can be doing. You can see that there isn't really a great discrimination power from the X-ray absorption alone. It kind of could match any of them. But when we look at the dichroism, that's where it becomes very clear that only the signal for the tetrahedral cobalt matches our signal. And so we can assign cobalt as being on those tetrahedral sites. Those are our pink sites. Okay. Then we have two more cations. Yeah.
So for the dichroism for the chromium, it seems like the peak or the dichroism around 590 or so is a bit weaker in the experiment than the theory. Where is there any explanation for that?
Yeah, so there are a variety of kind of complex effects that modulate the intensity of the L2 edge relative to the L3 edge. Actually, I'm not convinced that it's something that I fully understand, but I think it's commonly seen in a lot of different materials. Yeah. Okay, so our iron case. So iron as a cation, we know based just on its kind of chemical behavior that it has a possibility to be 2+ or 3+, and it also can be tetrahedral or octahedral. So again, this is a case where it's complex. Actually, the detailed modeling in the case of iron reveals that it has a 50-50 kind of split between tetrahedral and octahedral sites. So we can actually perform a detailed quantitative modeling of the data to arrive at that conclusion. And our most interesting cation is manganese. So manganese is what we call our shapeshifter in this material, because it turns out that to fully describe the spectrum of manganese, which as you can see at the top there, the blue line, it doesn't really match any of the individual calculated spectra. What it actually matches is a weighted sum of all three. So all three are present in manganese in different proportions. And when we look at the whole ensemble, once we've assigned all 5 cations to their positions, we can do some sanity checks. So we know that there has to be a 1:2 ratio of tetrahedral to octahedral. We know that overall the material has to obey charge neutrality, so the valences have to make sense. And when we do that, we actually do arrive at a consistent picture for how the cations are distributed in this material. So this is really amazing. From this type of local investigation of the individual cations, we can assign with pretty high certainty where these different elements are sitting and in what kind of proportion. So this is the end distribution. So again, it's kind of color-coded according to these 5 different elements. So our tetrahedral sites are more than half cobalt, whereas the octahedral site is much more random. It has 4 cations in kind of close to equal proportion. And so technically, if you kind of individually look at these 2 sublattices and calculate what their configurational entropies are, again, using that kind of Boltzmann formula, you end up somewhere kind of around here. So it's more in the medium entropy limit than the high entropy limit. But if you add both of those sublattices together, you would indeed end up well within the high entropy range. Okay, what time is it?
You're 15 minutes till the hour. But
Perfect.
15 minutes.
Yeah. Okay, I really just have one more thing I want to get to. So now we can zoom back out to the synthesis method dependence. So we fully characterize our one material. We know what its structure is, where the elements are sitting, what its magnetic behaviors are. Now we want to see how does the change of synthesis method influence how that material behaves. So from diffraction, we can ask, first of all, are there any differences just in the crystal structure of the material itself? And one of the ways we can parameterize this is through the oxygen coordinate. So that's an adjustable structural coordinate within our X-ray refinement. It tells us exactly where the oxygen sits. And in spinels, that oxygen coordinate specifically affects the relative size of the tetrahedral and octahedral environments. So if our oxygen coordinate is pushed in either direction, it means that there's a relative change in the size of those 2 environments. But overall, space is filled the same way. And what we see is that across the 5 methods, so here the color coding is always consistent. Yellow is always solid state and blue is always combustion. And what we see is that they're pretty much the same within error. They don't really differ from one another. And yeah, they have quite a tight tolerance. So first we would say the average structure is really not changed. And then we can consider the smallest possible length scale. So this is where we're going to go back to our X-ray absorption. And the cation that we can kind of pick out as the one that's most likely to have differences in its behavior is manganese, because manganese was our shapeshifter. And it had the most complex behavior in our original material. And so when we look at the shape of that absorption spectra for manganese, so this is just the L3 edge, what we see is that it's really, there might be very, very subtle differences in the shape, but the key features in that absorption spectra are maintained across all 5 samples. And we can even quantify this. So we can look at the relative weighting of those 3 different manganese valences. So we have divalent, trivalent, and tetravalent that are all present. And if we do a detailed weighting, which is achieved by these multiplet calculations, we see that there's a very small change as a function of synthesis method. So the manganese average valence is actually shifting up as we move towards the kind of more kinetic side of the spectrum, which may tell us something about possibly oxygen vacancies that exist in this material, but it's hard to be too concrete. We don't see any changes in any of the other 4 cations. The other 4 cations are really not changing. Okay, so far, these 5 samples prepared by 5 different synthesis methods really look kind of identical to each other. And it turns out that it's neither the very long length scales nor the very small length scales where the important differences emerge. It's actually at the intermediate length scale. So these are scanning electron micrographs of 3 of our samples. And actually the next characterization at UBC seminar is all about SEM. So I won't say anything about this technique, except to just say that it allows us to image our material at kind of micron length scales. And so it's like a photograph of our crystal, basically, with surface. And so what we see is that the microscopic morphology of our samples is actually really strikingly different based on the synthesis method. Our solid state sample looks like these kind of shaggy bits of rock. It has kind of rough surfaces. And our molten salt sample has these beautiful, well-formed micron scale crystallates that are even faceted. And combustion, that most rapid growth technique, forms this highly porous and networked solids. It's very low density. And the characteristic particle size in that combustion sample is kind of sub-micron. So they look very different, but are they different? So to answer this question, the final technique that I'll introduce today is X-ray microfluorescence. So again, this is an X-ray based technique. And the idea with a fluorescence measurement, so you might be familiar, there's laboratory X-ray fluorescence experiments. And the way that they work is kind of similar actually to how X-rays are produced in our copper anode X-ray source, is we knock out some core electron, and then various electrons can decay in to fill that lower energy position, and they all produce characteristic X-ray energies, and that's our fluorescence signal. So if you perform a fluorescence experiment on a sample, this is kind of a textbook fluorescence measurement where you can measure the spectral lines. This one has lead, argon, tin, lead, and they're different electronic transitions within that specific atom. So one important application of X-ray fluorescence is in cultural heritage, where because it's a non-destructive technique, you can learn about this doesn't show up quite so well. So this is a painting in the National Gallery in London. So it's like an old master's painting, and researchers were seeking to understand what type of pigment was being used, what were the kind of chemical constituents within that pigment. And so that's an application of X-ray fluorescence. But they're mapping out actually the whole painting, kind of on centimeter to millimeter scales. And what we want to know about is something at a smaller length scale. We want to know about chemical homogeneity differences at these micron length scales, where we actually see morphological differences. And so we can do exactly the same type of experiment, the same type of fluorescence experiment at a synchrotron, where taking advantage of the fact that we have this extremely brilliant source of X-rays, we can focus it down to really small sizes. we can actually raster across a sample in kind of micron scale step sizes to learn about the chemical homogeneity of the material. So the beamline that we did these experiments at is called ID21, and it's at the European spallation source. Okay. And so here is the final result that I will share today. These are our X-ray fluorescence micrographs. And so how do you understand these? So this is our legend. Our legend here is kind of a tripartite representation of 3 elements. 3 are just chosen for illustrative purposes. It's actually, with this type of imaging, not possible to look at more than 3. So we have selected out manganese, cobalt, and iron, 3 of our 5 cations. And the way these images are rendered is that every single pixel in this image represents one unique measurement, and it's a length scale of order a micron. So we're going across the sample micron by micron. We're measuring the fluorescence signals of those 3 cations, and then we're looking at how proportional they are to one another. Are they in equal proportion? If they are, that takes us to the center of this triangle, which is gray. Whereas if I have an excess of manganese relative to cobalt and iron, I'm going to see a blue pixel. Likewise, an iron pixel is going to be green and a cobalt pixel is going to be red. It's not telling us that only that element is just simply that it's present more than the other 2. So it's kind of disproportionately present. And likewise, we can get purple, yellow, or cyan, depending on specific mixtures of the cations that occur. And here we can appreciate that there's a really substantial difference from these 3 synthesis methods. Our solid state sample is kind of macroscopically homogeneous. It has these big pink regions, these big blue regions, and then little bright, extremely iron-rich regions. And this makes sense to us because solid state synthesis is a diffusion-limited process. So it doesn't have that initial impetus to become highly randomized. And so it makes sense based on the synthesis method that there might be micron scale inhomogeneities in how the cations actually manage to migrate into the material. And in molten salt synthesis, what we actually see is that iron is heavily abundant everywhere. And this we can correlate again to the synthesis method. We know that the different precursors that we use in this molten salt method have different relative solubilities within the salt. It's very natural that one may selectively precipitate out more than the others. And so overall, molten salt is actually not producing a completely stoichiometric material. It's deviating from that perfect kind of equal parts of each cation. And then our final sample, which is our combustion sample, that's that violent explosion that we saw. This is our best representation of what a high entropy oxide should be. Every pixel in that image is in the gray sort of spectrum range, ranging from white to black, telling us that there's no micron scale region of this sample where any one cation is more abundant than any other. This material is truly homogeneous, which is the limit that best reflects what we want a high entropy oxide to be. We want them to have this full randomness. Okay, so let me just bring up my conclusions. So yeah, I've shown you just kind of a smattering of the work that our group has done on high entropy oxides up to this point. We've been working on this topic for about 6 years now. We found them to be a really exciting platform to study very fundamental questions in material science. And they have led us to try out a lot of new characterization techniques that we weren't already using, many of which I haven't discussed today, and also including computational methods. I would really like to highlight Solvay, who's in the audience, who is a postdoc in my lab who's led a lot of our high entropy work, and also Mario Gonzalez-Rivas, who's a PhD student who has done a lot of the X-ray spectroscopy that you saw today. And thank you so much for your attention. And I guess I meant to advertise that
Good.
the next seminar is on the aforementioned electron microscopy.